So far, for our surfaces, we've dealt with a specific parameterization. But as you know, there's more than one way to parameterize a surface, or anything. And so now we have the same example. We have D being the unit disk, and we have a parameterization of the cone using that disk, and we orient it with an outward pointing normal vector. Okay, so then we want to find the flux across this across the surface here, given this parameterization. So again, we can do the calculation, and here we'll just go through it briefly. So Tx, you end up with 1, 0, and then x squared plus y squared, and then to the minus 1/2 after you simplify, and then ty, you end up with 0, 1, and then y, x squared plus y squared to the minus 1/2. Okay, and then when you cross them, tx cross ty, we end up with something that's a little nasty, but we'll deal with it. So we end up with negative x over square root of x squared plus y squared, negative y over square root of x squared plus y squared, and then 1. But so this is nasty, but then when we look at the flux, so integral over y, or double integral over y of f dot ds, d big S. Okay, so f is just this, and then we have to dot it with the normal vector, right? And here, so when we dot that, it would just be the first two components would be eliminated. It would be just 1, but then we have to remember that we have to check orientation, and we do want this oriented outward, and it happens to be, and you can verify that if you look at the orientation of this vector, that this is an inward pointing normal vector, and so then when we do this, we just have to account for that opposite sign. So this is going to be the double integral over d of negative 1 and then dx dy. Okay, and then when we do this, again, so this would be minus 1, and then double integral over d dx dy, dx dy, let's erase that, dx dy, and so we get negative 1, and then area of the disk of the unit disk is pi, so we get minus pi. So the same thing as before, right? And so you're thinking, oh, well, yeah, we should have expected that, right? And the idea here is that we implemented a reparametrization, or we hope there is a reparametrization. So we have a parameterized surface from before, that was our previous example, and then we have a new parameterization, y, that we implemented here, and what we hope is that there's a one-to-one and onto function, that is, meaning it's really bijective, that it's invertible, such that when we look at the parameterization of y, there's some way to get from x to y via this function of h. Okay, and then if there is, then we end up with some nice conclusions. So if we have a one parameterization and a second parameterization, then if there is this one-to-one mapping, then, well, we can certainly say that the vector, or the scalar surface integrals, g ds, is equal to the surface integral over with the y parameterization, g ds. Okay, that's nice. Okay, we can also say two more things. We can say that if we look at the flux for each, okay, so here's f dot ds, and here is the flux under y, or using the y parameterization, f ds. Okay, and there's actually two cases of this, so I'll write this out. F ds and y f dot ds, and I should have a vector over the s's as well. Okay, so when comparing the flux, if x and y have the same orientation, then you might expect that their flux are the same. Fluxes. We're going to say fluxes. But the flux under each parameterization should be the same. If the two parameterizations have opposite orientation, then you might expect, well, if it's opposite, one of them needs to be minus, so that is precisely true. Okay. So the upshot here is maybe in some cases maybe you and your friend are working and you parameterize the surface differently, but it's still correctly. You should ultimately get the same answer or the same value for at least, well, for each of these, as long as you take into account orientation. All right, and that's going to wrap up videos for surface integrals this week. We'll see you in class.